Polymer film preparation methods, principles, processing, and structure property relationships. Polymer films represent a fundamental class of materials in modern science and engineering, characterized by low density, mechanical flexibility, chemical resistance, and highly tunable physical properties. Since the mid-20th century, continuous advancements in polymer chemistry, synthesis, and processing technologies have significantly expanded the performance and functional scope of these materials. As a result, polymer films have become indispensable in a wide range of applications, including microelectronics, packaging, optical systems, energy devices, and biomedical technologies. The performance characteristics of polymer films, such as mechanical strength, optical transparency, thermal stability, and electrical behavior, are not governed solely by polymer composition, but are strongly influenced by fabrication methodology. Film preparation techniques determine molecular chain arrangement, crystallinity, defect formation, and interfacial interactions, thereby establishing critical structure property relationships. Consequently, a comprehensive understanding of film preparation processes is essential for both fundamental materials research and industrial-scale manufacturing. This report provides a systematic and descriptive analysis of major polymer film fabrication methods, including solution casting, spin coating, and hot pressing, together with emerging techniques. Emphasis is placed on their processing principles, operational procedures, material compatibility, and the resulting advantages and limitations. General considerations in polymer film preparation. Polymer film preparation involves the transformation of polymeric materials into thin, continuous layers with controlled thickness, morphology, and functional properties. The quality and performance of the resulting films are determined by several interrelated factors. Polymer characteristics such as molecular weight, chain architecture, degree of crystallinity, and thermal transitions, including glass transition and melting temperatures, play a central role in defining processability and final film properties. In addition, rheological behavior, particularly viscosity and viscoelasticity, governs the flow, leveling, and uniformity of the film during formation. In processes involving solvents, solvent properties such as volatility, solubility parameters, and interactions with polymer chains significantly affect film formation and microstructure. Processing conditions, including temperature, pressure, shear forces, and solvent evaporation rates, must be carefully controlled to achieve the desired film characteristics. The nature of the substrate, including its surface energy, roughness, and chemical compatibility, also influences adhesion and uniformity. Environmental conditions such as humidity, odd airflow, and contamination further contribute to variability in film quality. Film formation typically occurs through mechanisms such as solvent evaporation leading to polymer precipitation, thermal softening or melting followed by solidification, mechanical deformation that induces molecular orientation, or field-driven deposition processes such as centrifugal or electric forces. Through precise control of these parameters, it is possible to tailor film thickness over a wide range from nanometers to millimeters, as well as to manipulate morphology, ranging from amorphous to highly crystalline structures, thereby optimizing functional performance. Major polymer film preparation methods. Solution casting. Solution casting is one of the most classical and widely employed methods for polymer film preparation. It involves dissolving a polymer in a suitable solvent to form a homogeneous solution, which is then deposited onto a substrate and allowed to dry, resulting in film formation. The underlying principle is based on solvent evaporation, during which polymer chains gradually reorganize and solidify into a continuous film structure. The kinetics of solvent evaporation play a decisive role in determining film morphology. Rapid solvent evaporation can lead to the formation of pores, surface roughness, and internal stresses, while slower evaporation facilitates molecular chain rearrangement, resulting in denser films with improved mechanical properties. Film thickness is primarily governed by the solution concentration, casting volume, and substrate dimensions. The preparation process typically begins with the dissolution of the polymer using stirring or ultrasonication to ensure homogeneity. The resulting solution is then uniformly spread onto a clean substrate. Controlled drying under defined temperature and humidity conditions allows solvent removal and film formation. Finally, the dried film is carefully removed from the substrate. Throughout this process, strict environmental control is required to minimize contamination and defects. Solution casting applies to a wide range of soluble polymers, including polyesters, polyamides, polymethyl metaacrylate, polyvinyl alcohol, and polyvinyl chloride, as well as functional polymers such as conductive or biodegradable systems. The method offers significant advantages, including simplicity, low cost, compatibility with thermally sensitive materials, and the ability to incorporate additives or fillers. However, it also presents limitations, such as sensitivity to solvent evaporation conditions, potential for defects, residual solvent effects, long processing times, and environmental concerns associated with solvent use. Spin coating. Spin coating is a widely used technique for producing thin polymer films with high uniformity and controlled thickness. In this method, a mixture of polymer solution is deposited onto a substrate that is rapidly rotated. The centrifugal force generated during rotation spreads the solution evenly across the surface, while simultaneous solvent evaporation leads to rapid film formation. Film thickness in spin coating is primarily determined by spin speed, solution viscosity, and spinning duration. Higher spin speeds generally result in thinner films. This technique is particularly suitable for producing films with thicknesses ranging from nanometers to micrometers. The process begins with the preparation and filtration of a homogeneous polymer solution to remove impurities. A small volume of the solution is then dispensed onto the center of a clean substrate. Upon rotation at high speed, the solution spreads outward and forms a uniform layer. Post-treatment steps such as thermal or vacuum drying are often employed to remove residual solvent and enhance film stability. The entire process must be conducted under controlled environmental conditions to ensure reproducibility. Spin coating is compatible with a variety of polymers, including polymethyl metaacrylate, polystyrene, polyvinyl alcohol, polyimides, and conductive polymers. It offers advantages such as excellent thickness control, smooth and uniform films, rapid processing, and efficient material usage. However, it is limited by substrate size and geometry, is less suitable for large area coatings, and may introduce thickness gradients and internal stresses due to rapid solvent evaporation. Hot pressing. Hot pressing is a thermomechanical technique that involves heating polymer materials above their glass transition or melting temperature and applying pressure to form dense films. Under these conditions, polymer chains gain sufficient mobility to flow and conform to the mold geometry. Subsequent cooling under pressure solidifies the material into a uniform film. The process begins with the preparation of polymer material in forms such as powder, pellets, or preformed sheets. The material is then placed in a mold and heated to the desired temperature. Pressure is applied to shape the material into a film, followed by controlled cooling to fix the structure. After cooling, the film is removed and may undergo additional finishing processes. Precise control of temperature and pressure is critical to achieving uniform thickness and optimal properties. Hot pressing is primarily applicable to thermoplastic polymers such as polyethylene, polypropylene, polycarbonate, polyamide, and polyvinyl chloride, as well as composite systems. The method offers several advantages, including solvent-free processing, high-density films with excellent mechanical properties, and suitability for large-scale production. However, it requires significant equipment investment, is limited to heat-processable materials, and may induce thermal degradation or internal stress if not properly controlled. Compression molding is a widely used thermomechanical processing technique for producing dense polymer films and sheets, particularly from thermoplastic materials and certain thermosetting systems. It is closely related to hot pressing, but typically emphasizes mold-based shaping under controlled pressure and temperature to achieve uniform thickness and high structural integrity. Extrusion is one of the most important and widely implemented industrial techniques for producing polymer films, particularly for large-scale, continuous manufacturing. It is a melt processing method in which polymer materials are heated, melted, and forced through a die to form films of controlled thickness and width. Due to its high productivity, scalability, and compatibility with a wide range of polymers, extrusion plays a central role in packaging, electronics, and functional film industries. Other polymer film fabrication techniques. In addition to the primary methods, several alternative techniques have been developed to address specific application requirements. Spray coating involves atomizing a polymer solution or suspension and depositing it onto a substrate, making it suitable for large area or irregular surfaces. Mechanical stretching is applied to preformed films to induce molecular orientation, thereby enhancing tensile strength and anisotropic properties, particularly in packaging applications. Electrospinning utilizes a high-voltage electric field to draw polymer solutions into nanofibers, forming porous membranes with high surface area, which are widely used in filtration, sensing, and biomedical applications. Structure-property relationships. The preparation method has a profound impact on the microstructure of polymer films, which in turn determines their macroscopic properties. Crystallinity is influenced by cooling rates in thermal processes such as hot pressing and by solvent evaporation rates in solution casting. Chain orientation can be induced by shear forces during spin coating or by mechanical stretching. Porosity and defect formation are largely governed by evaporation kinetics and process stability, while residual stresses arise from rapid solvent loss or uneven thermal gradients. These microstructural characteristics directly affect mechanical strength, modulus, optical clarity, refractive index, barrier performance, and electrical conductivity in functional films. Therefore, controlling processing conditions is essential for tailoring film properties to meet specific application requirements. Research significance and future perspectives. A systematic understanding of polymer film preparation methods provides significant theoretical and practical benefits. From a scientific perspective, it enables deeper insight into the relationship between processing conditions and molecular organization, thereby supporting the rational design of advanced materials. From an engineering standpoint, it facilitates the selection of appropriate fabrication techniques, optimization of production processes, and improvement of product performance. Future developments in polymer film preparation are expected to focus on environmentally friendly and solvent-free processing technologies, precise nanoscale thickness control, and the development of advanced functional films such as conductive, biodegradable, and stimuli-responsive materials. Integration with emerging technologies, including flexible electronics and energy systems, as well as the advancement of scalable and high-precision manufacturing techniques, will further expand the role of polymer films in modern technology. Conclusion. Polymer film preparation represents a critical link between molecular design and practical application in materials science. Techniques such as solution casting, spin coating, and hot pressing each offer distinct processing advantages and limitations, making them suitable for different material systems and performance requirements. Additional fabrication methods further enhance the versatility of polymer film production. A thorough understanding of processing principles and structure-property relationships is essential for the development of next-generation polymer films with tailored functionalities. Continued advancements in materials design and processing technologies will ensure that polymer films remain integral to progress in electronics, energy, healthcare, and sustainable engineering.